In the body, pH affects everything from cardiac contractility to enzyme function. Not surprisingly, the body's acid-base status is tightly regulated by various systems to keep the pH within that sweet, sweet Goldilocks zone. But, as is the theme in this course, pathology rears its ugly head and shoves either acids or bases out of balance. And in response, the body tries as hard as it can to compensate. In this sketch, we'll figure out whether we're dealing with an acid or base problem, and whether it's stemming from a breathing problem, aka respiratory, or an issue with ingesting, metabolizing, excreting, vomiting, or pooping acids and bases, aka metabolic. For that, we must take a journey to the land of Moracid. Here, we'll meet PHrodo on his quest to restore the balance. You see, he has severe diarrhea, and therefore bears an excess of protons that weighs down his very soul. In trousers. His uncle bestowed upon him this diarrhea on the night of his name day, lest he succumb to the acidosis, for he could not adequately compensate with increased respirations. Probably because of all that pipe weed he was smoking. And so PHrodo set out to destroy the diarrhea. At the forges of Mount Acid, armed with only a dagger and a formula. A gift from Lady Winter. All right, we're going to play all-seeing eye here for a moment. Let me point out some of the landmarks here in Moracid. To detect an acid or base disturbance in your patient, you need to get an arterial blood gas, or ABG. A standard ABG tells you the pH, CO2 level, and calculated bicarbonate level. A normal arterial pH is around 7.4. A normal CO2 is around 40 millimeters of mercury, and a normal bicarbonate is around 24. Let's start with pH. Acidosis means your pH level will be low, less than 7.35. Here in Moracid, all the pathologies causing acidosis, whether metabolic or respiratory, will be placed low in the scene, where the dangerous acid lava flows. Remember, low in the scene means low pH. Alkalosis means your pH will be high, greater than 7.45. On test day, think of the upper half of the scene, where the pathologies causing alkalosis roam the mountainside, next to those brilliant blue basic pools. Again, that's high in the scene for high pH. We're going to head first to the bottom of the scene, however, as our journey begins with acidosis, the cause of which can be divided into respiratory or metabolic processes. And as we focus in on PHrodo's travel companion, Gap-wise, I think it's pretty obvious which category we're starting with. Stuffing his face, as usual. In this scene, that's our theme for metabolic processes. So back to that ABG. The three values we care about are pH, bicarb, and CO2. pH we've already discussed. We're acidotic, so we expect the pH to be low, which is why we're low into the scene. Next, bicarb, the most important component of the pH buffering system of the body. This is how your body resists pH changes. And in the setting of metabolic acidosis specifically, what we're doing is disturbing that right side of the equation, causing bicarbonate levels to decrease. As we'll soon illustrate, we can do this by adding a bunch of acid to the system, causing the buffering equilibrium to shift to the left, thereby decreasing bicarb. This is what happens when your patient is in ketoacidosis, or ingests methylene glycol. Alternatively, we can directly drop bicarb. In most cases, when a bicarb is lost, its corresponding proton is retained. This is accomplished either by excreting bicarb in an excessive amount of diarrhea, or with the kidney abnormality that decreases bicarb reabsorption or production. Yep, the kidney can actually make brand new bicarb. When it's not broken, that is. All right, back to the scene at hand. Metabolic acidosis is characterized by a decrease in bicarb, as depicted by the bicarbonate baking soda tumbling out of Gapwise's pack as he traverses the gap. There's one more part of the ABG we haven't discussed yet, and that's PaCO2, a measure of the amount of dissolved carbon dioxide in the blood. This value is predominantly controlled by the lungs. Increase ventilation and you breathe off CO2. Decrease ventilation and CO2 accumulates. But wait, metabolic acidosis has to do with peeing and pooping and eating and stuff. You didn't say anything about breathing? Well, the other half of the story is about compensation. In the setting of metabolic acidosis, when that H+ is accumulating, the lungs kick in, increasing ventilation and blowing off CO2. This helps move that equilibrium even further to the left. thereby decreasing that H plus back toward normal. The theme of these compensatory mechanisms is that they never quite get the pH back to baseline, but they try. All right, we're acidic here. The lungs are trying to help out, so they blow off more CO2, trying to raise that pH a little, you know? This is called a compensatory respiratory alkalosis, characterized by decreased PaCO2, and symbolized here by carbon fumes that are low to the ground. Remnants of that morning's breakfast, I'm guessing. Come on, guys, you gotta cover your tracks better than that. By the way, as the sketch progresses, we'll always match each primary acid-base disturbance with its compensatory mechanism. This will be reflected in the partially compensated lab values. And in metabolic acidosis, that means low pH, low bicarb, and low compensatory CO2. The next step in diagnosing the cause of metabolic acidosis is to look at a little thing we in the land of Moracid call the anion gap. Remembering back to our sketches on volume disorders, if you watched it, that is. And shame upon your house if you didn't. There are major anions and cations in all fluid compartments of the body. From a pure chemistry perspective, the sum of all the negative charges, or anions in the body, must equal all the positive charges, or cations, to maintain isoelectricity. Which sounds a lot cooler than it is. The extracellular space, and therefore the blood plasma, is dominated by three ions: the cation sodium and the anions bicarbonate and chloride. That said, there are many more ions and negatively charged molecules, such as albumin, that don't exist in as high of a concentration, but still play incredibly important roles. And we just kind of shove them all into that orange box up there. That's the anion gap. Put it another way, we can calculate the anion gap by subtracting the plasma bicarbonate and chloride concentrations, the anions on the right, from the plasma sodium concentration, the cation on the left. The normal anion gap is around 8 to 12. In this scene, the equation for the anion gap is depicted on this message carved into the stone next to the gap. None shall cross. Notice how the N-H-C is highlighted. To remind you of sodium minus bicarb minus chloride. There are two doors to choose from in metabolic acidosis: normal anion gap or increased anion gap. Let's see what kind of acids can increase that gap. This means that there are a significant number of other negative charges floating around. You can think of increased anion gap metabolic acidosis as being caused by a preponderance of sneaky, unmeasured organic acids driving the bicarb down. This makes even more sense when you think about that isoelectric concept. If bicarb and anion is low, there must be other negative charges, aka organic acids, there to take its place, since the total number of cations hasn't changed. Arithmetic-wise, if you subtract the bicarb and chloride from the sodium and you get a value over 12, think anion gap acidosis. In this scene, to depict increased anion gap metabolic acidosis, we have Frodo's travel companion here jumping that gap. Notice, too, that the supplies on the side of his travel pack evoke an image of values greater than 12. The sneaky acids increasing that gap can all be remembered by the helpful acronym MUDPILES, which stands for methanol, uremia, diabetic ketoacidosis, propylene glycol, iron and isoniazid, lactate, ethanol and ethylene glycol, and salicylates. Oh, shoot. Looks like one of the Gorks has captured osmole, as the Gork rummages through the dwarf's things and waits for him to marinate. Let's go through the causes of increased anion gap metabolic acidosis, starting with the M in MUDPILES, methanol, present in windshield washer fluid, sterno, and solvents for paints. Why osmole brought it along? Only one can guess. After ingestion of methanol, it's converted into formic acid by alcohol dehydrogenase. Formic acid damages the optic nerve and can make you go blind. So be careful about methanol byproducts contaminating that dwarven moonshine. Next up, the U in MUDPILES, uremia. Measured on labs as increased blood urea nitrogen, or BUN. You see, dwarves are known for two things. One, their love of gems and precious metals. And two, their love of fast food. BUN is a component of renal azotemia. When BUN and creatinine increase in the serum due to acute or chronic kidney disease and decreased GFR. In the setting of decreased kidney function, however, it's not just urea that builds up in the serum. The kidney also has trouble filtering out other organic acids and waste products such as sulfuric acid, phosphoric acid, and uric acid. Remember, this is why we installed that acid volcano at the Chronic Kidney Disease Museum. Metabolic acidosis, here we come. The D in MUDPILES is for diabetic ketoacidosis, or DKA, symbolized by a locked candy jar that can only be accessed with a delicious candy key. A ketone key, if you will. DKA is an acute complication of type 1 diabetes. Over in the endocrine unit, we'll portray the ketones as the winnings at the end of the Candy 200 race. Two ketones in particular will be portrayed by acidic sour candies: the organic acids acetoacetate and beta-hydroxybutyrate. Be sure to check out that video for more info on the pathogenesis of DKA. Go ahead. What are you waiting for? Wait, no, not right now. I miss you already. Other conditions can cause the buildup of ketones as well, including alcoholism, starvation, or a ketogenic diet. So watch out. All right, time for the P in piles: propylene glycol. Like methanol, this alcohol can be found in various products, including antifreeze. It's also metabolized into acid by alcohol dehydrogenase. Again, not really sure what OSMLE had in mind there. Maybe like a solvent for something? Moving on. The I in mud piles is for iron and isoniazid. Acute iron poisoning can cause an anion gap metabolic acidosis when ferric ions get hydrated and release protons. And isoniazid we met in Sketchy Farm. It's our isolate ranger used as a component of RIPE therapy for the treatment of tuberculosis. It can cause numerous neurologic side effects, including seizure, which leads to lactic acidosis. A perfect segue into the L in mud piles: lactic acid, represented by OSMLE's expired, undoubtedly acidic milk. Lactic acid builds up in times of hypoxia, like during that seizure we just mentioned. Cells switch over to anaerobic metabolism, which means lactate production and metabolic acidosis. Alcoholism is another famous cause of lactic acidosis. An overworked alcohol dehydrogenase results in excess NADH, which drives the production of even more lactate. The E in mud piles is ethylene glycol, the main component of antifreeze. Again, like we saw with the other alcohols, it's metabolized by alcohol dehydrogenase into acid. Oxalic acid, particularly, likes to combine with calcium and precipitate in the renal tubules, causing obstruction. So many reasons not to ingest antifreeze. And finally, the S in mud piles: salicylic acid, also known as aspirin. At Sketchy, our symbol for aspirin is the ASA umpire. And in this scene, we've incorporated an umpire's gear into the armor worn by the Gork. Not only is salicylic acid an acid, it's toxic to mitochondria, leading to tissue hypoxia and lactic acidosis. Whew, boy, big list, right? Many of these substances are associated with specific clinical presentations and laboratory profiles which are beyond the scope of this sketch. However, to narrow down the differential just a little bit, we can calculate the osmolal gap. It turns out that methanol, propylene glycol, and ethylene glycol aren't just acids. They're also active osmols and affect the calculation of serum osmolality. Having trouble deciphering the mysterious equation on the wall there? It's an ancient language called algebra. Don't worry, we can solve this riddle together. Just know that the most important osmol in the plasma is sodium, multiplied by 2 because it's associated with some sort of counter anion. Glucose, BUN, and ethanol can also contribute to the serum osmolality, especially during times of hyperglycemia, uremia, and acute alcohol poisoning. But under normal circumstances, sodium is the main component. Now, an osmol gap is exactly what it sounds like. The equation above gives you the calculated osmolality. Subtract this from the actual osmolality you get back from the lab, and you'll notice a gap. There are some extra osmols that we're not accounting for. Normally, this gap is pretty small, less than 10. But throw methanol, propylene glycol, and ethylene glycol into the mix, and now you have a bunch of extra osmols and the gap increases. To remind you of an osmolal gap greater than 10, we've placed OSMLE above his trusty axe and shield, forming a 10 shape. And to remind you that specifically methanol, propylene glycol, and ethylene glycol act as osmols to increase the gap, we've highlighted the E, P, and M on the conned osments that the Gork is using for his basting sauce. And there you have it, increased anion gap metabolic acidosis. Low pH, low bicarb, and a compensatory decrease in carbon dioxide. Use the anion gap equation to calculate a gap greater than 12. And sometimes use the osmolal gap equation to see if methanol, propylene glycol, or ethylene glycol is involved. All right, a little twist in the story here. What if the anion gap is less than 12? Simple. We just call it a normal anion gap metabolic acidosis. So let's leave the gap behind and catch up with PHrodo. Again, we've got decreased pH, decreased bicarb, and a compensatory decrease in CO2. But this time, there are no extra sneaky organic acid ions floating around. Instead, the acidosis is caused by a disproportionate loss of bicarb or an inability of the kidney to reabsorb or regenerate it. Remember, in most cases, when a bicarb is lost, its corresponding proton is retained. Let the acidosis begin. Normally, when bicarb anions go down in the serum, chloride increases correspondingly, thus maintaining isoelectricity. See? As that blue box gets smaller, the yellow chloride box takes its place, and the anion gap stays the same. This is also known as a hyperchloremic normal anion gap metabolic acidosis, hence the accumulation of chloride crystals above pHrodo. All right, let's look at a couple of ways we can decrease bicarb. First, pHrodo's main affliction, that excessive diarrhea. It turns out that severe poopy times can cause metabolic acidosis because of a loss of large amounts of bicarbonate-rich pancreatic secretions. I feel it in the water. I feel it in the earth. I smell it in the air. I feel it in my pants. Bicarb that once was lost. Precious bicarb.
My precious.
Whoa. Calm down, everyone. It's just diarrhea. And as he pulls out that renal tubular vial to light his way, a gift from Lady Glamurdriel, think of renal tubular acidosis, or RTA, a group of disorders that results in decreased reabsorption of bicarb by the kidney, or a decreased production of bicarb by the kidney, which is paired with the inability to properly excrete H+. You'll encounter a few pathologies throughout this course that affect renal handling of bicarb, like adrenal insufficiency. For more info on RTA, check out their very own sketch coming up next. All right, that's it for metabolic acidosis. Let's keep the acidosis party going with the other form. Respiratory acidosis. Enter SMEGASP, the fellowship's reluctant guide. Though can't say he's been that helpful so far. He's either talking to himself or arguing with his reflection or just strangling himself. Look there, see? He's doing it again. What is he, suffocating himself? I just don't get that guy. Needless to say, SMEGASP is going to embody all that is respiratory acidosis. So back to that ABG. The three values we care about are pH, bicarb, and CO2. We're acidotic, so expect the pH to be low, which is why we're low in the scene. This time we're going to look at PaCO2 next. This value is predominantly controlled by the lungs. Increase ventilation and you breathe off CO2. Decrease ventilation and CO2 accumulates. And that's exactly what's happening in the setting of respiratory acidosis. We're decreasing ventilation and allowing CO2 to accumulate. This pushes the equilibrium to the right, toward more H+ and acidosis. All right, back to the scene at hand. Respiratory acidosis is characterized by an increase in PaCO2, as depicted by the carbon fumes rising high into the air from the active campsite. Why did pHrodo and company have to scramble away from the campsite so quickly? Well, that brings us to the third part of the ABG, bicarb. This value is predominantly controlled by the kidney, which can excrete, retain, or produce new bicarb as needed. But wait, you said respiratory acidosis, not renalatory acidosis. Remember, we're always going to pair the primary acid-base disturbance with the corresponding compensatory mechanism. In the setting of respiratory acidosis, when that H+ is accumulating, the kidneys kick in, increasing not only bicarb retention, but bicarb production. Yeah, it can make new bicarb, with the corresponding proton excreted in the urine, of course, thereby decreasing H+ to decrease acidity. These compensatory mechanisms never quite get the pH back to baseline, but, they try. The kidneys are pretty slow too, and this response can take days. Shh. Roost on my face and call me a radicast. It's another cork. See how he's lifting that bicarb baking soda from the travel pack? That stands for increased bicarb. So to recap, in respiratory acidosis, we see low pH, high PaCO2, and a compensatory increase in bicarb by the kidney. All right, let's take a look at a few pathologies that cause patients to retain CO2. First, COPD, as portrayed by that big, blue, bloated, chronically obstructed gork. Patients with COPD chronically retain CO2 due to decreased respiratory drive and impaired gas exchange. For more on COPD, check out the street hockey sketch in the pulmonary unit. Shh, he's moving. No? Oh, phew. Anywho, another cause of CO2 retention includes obstructive sleep apnea, which causes obstructive sleep apnea and hypoventilation at night. Next, how about instead of obstructing ventilation, we decrease the drive to ventilate? This can occur with drugs such as opioids and other sedatives that act as central nervous system depressants. Decreased drive means retained CO2. Man, Breathalyst saves the day again with that sleeping potion. Using his Using his alphanoid sneaky powers. Nailed it. For the next cause of respiratory acidosis, let's look back at poor Smegasp, who was put back in his chains. Guess he ran off one too many times. At Sketchy, a lock around a chest is our symbol for restrictive lung disorders, which include intrapulmonary disorders, such as pulmonary fibrosis, or extrapulmonary disorders, such as scoliosis, obesity, and pleural effusion. All of these conditions restrict lung movement, thereby impairing ventilation. So expect some CO2 retention. For more info on restrictive lung disease, head on over to the Pulm unit. Another way we can restrict ventilation is by inhibiting the muscles of respiration. See those neuronal dangly bits on Smegasp's unsightly loincloth? Let it remind you of neurological disorders, such as ALS, Guillain-Barré, polio, myasthenia gravis, and botulism that interrupt nerve transmission to the diaphragm. Notice, too, that Smegrasp has frail, atrophied muscles. Think of disorders such as muscular dystrophy, when their diaphragm is just too weak to ventilate. Whew, a couple of close calls there. We got through respiratory acidosis. Remember, that's decreased pH, increased PaCO2, and a compensatory increase in bicarb. All right, time to shift our focus to the top of the sketch, where a couple of Frodo's companions are having a gork problem of their own. But before we head up there, remember that high in the sketch means high pH. We're talking about alkalosis. Just like the acidic chapter of the story, alkalosis can be divided into respiratory and metabolic processes. Take a look at our next gork, enjoying a fresh fish head from the alkaline pools. Again, I think it's pretty obvious which category we're starting with. Munchin is our symbol for metabolic processes. So back to that ABG. The three values we care about are pH, bicarb, and CO2. pH we already discussed. We're alkalotic, so expect the pH to be high, which is why we're high in the scene. Next, let's look at bicarb. The pathologies we'll encounter in metabolic alkalosis all involve increased retention or increased production of bicarb. In most cases, a retained bicarb means a corresponding excreted proton. It's basic science. Basic. So notice that the metabolic alkalosis scene takes place next to the gork rummaging around the active campsite. Bicarb will be increased. The last part of the ABG is PaCO2. In the setting of metabolic alkalosis, compensation comes from the lungs. By decreasing ventilation, we can increase the amount of CO2 in the blood. See how that shifts the buffer system to the right? Adding more H+ to the system? This is how your body tries to fight off metabolic alkalosis, even though it never fully compensates. This is called a compensatory respiratory acidosis, characterized by increased PaCO2 and symbolized here by the carbon fumes rising high into the air from that active campsite. In summary, metabolic alkalosis is characterized by elevated pH, elevated bicarb, and, if there's compensation by the lungs, an elevated CO2. All right, so what are some examples of increased retention or increased production of bicarb? How about, say, vomiting after eating a slimy fish head from the alkaline pool? Vomiting leads to a loss of HCl from the stomach. And remember how those proton pumps work at the gastric mucosa. For every proton lost in the vomit, there's a corresponding bicarb molecule retained by the body. Sounds like alkalosis to me. Diuretics can also increase bicarb and cause metabolic alkalosis. With loop and thiazide diuretic use, reabsorption of sodium and chloride are reduced. Check out the loop and thiazide diuretic Sketchy Farm sketches for more details. But remember, when you block reabsorption of sodium and chloride in the more proximal segments of the nephron, it all passes to the distal nephron instead. Increased sodium delivery to the collecting duct causes increased NaH+ exchange. That's reabsorption of sodium and excretion of H+ into the urine. You know how that goes. Every H+ excreted means a bicarb retained. That H+ had to come from somewhere, right? You know what? It's not like we're in end-stage renal disease or something. Why can't the kidney, which is usually really good at handling bicarb, I've heard, just dump it all into the urine? correct the alkalosis and call it a day. Well, it's not that simple. Turns out that both the conditions we just described have a maintenance phase that impairs the kidney's ability to dump bicarb, forcing the body to stay alkalotic. Dang. There are actually many mechanisms thought to play a role. Take volume depletion, for example. I mean, we're peeing and vomiting a lot, right? Hypovolemia stimulates the renin-angiotensin-aldosterone system, which tells the kidney to reabsorb sodium in bicarb and excrete H+. Angiotensin has this effect at the proximal tubule, while aldosterone drives this process at the distal tubule. Wait, excrete even more H+? All so we can conserve all that sodium? Fine. There are even more complicated mechanisms involved. But suffice it to say, if we restore volume, we can reverse these annoying H+ excreting processes that are being driven by hypovolemia. This is called chloride-sensitive alkalosis. As in, if we give normal saline, which contains sodium chloride, and get them back up to euvolemia, say goodbye to alkalosis. This is illustrated by Poppin' up top, about to end this alkalosis gork party with a boulder. A bolus, if you will, of chloride crystals. Notice, too, the water bottle on the side of his travel pack, reminiscent of an IV saline bag. By the way, these conditions are associated with chloride depletion, too. With vomiting, the chloride is lost as hydrochloric acid. And in diuretic use, the chloride is excreted with the other ions. So the chloride in the isotonic saline corrects the chloride deficit in these patients, too. It's a win-win-win. Volume, chloride, and pH restoration. We're going to illustrate one more way to abnormally increase that bicarb. Mineralocorticoid excess, symbolized here by that huge mineralocorticoid mineral crystal. Mineralocorticoids, such as aldosterone, work at the collecting duct to increase sodium reabsorption, potassium excretion, and, there it is again, H+ excretion. For every H+ ion lost at the collecting duct, a bicarb molecule is retained. And there you have it, metabolic alkalosis. Mineralocorticoid excess is seen in primary hyperaldosteronism, congenital adrenal hyperplasia, and Cushing syndrome. Go rummage around the Sketchy endocrine unit for all the salty deets. Also, keep in mind that sodium retention at the collecting duct means volume retention. So, because we're volume expanded, none of those silly alkalosis-maintaining hypovolemia mechanisms are at work. Adding saline won't do a thing. Hence the name, chloride-resistant metabolic alkalosis. Well, good thing Poppin came through with that crystal rock to the PP, because that was taking a turn for the moist. In summation, metabolic alkalosis involves an elevated pH due to increases in bicarb with a compensatory increase in PaCO2 due to hypoventilation. All right, last but not least, respiratory alkalosis. You know what that means. Elevated pH. So we're staying high in the scene. Time to catch up with Murray at the top of the alkaline falls, trying desperately to get a signal to their wizard friend, Randolph the Beige. Notice that Murray is holding our recurring Sketchy symbol for respiratory alkalosis, a hydroxyl-shaped bubble wand. Just think about how much hyperventilation it takes to keep that signal going. So one more time, let's look at that ABG. Remember, the three values we care about are pH, bicarb, and PaCO2. We're alkalotic, so we expect the pH to be high, which is why we're high in the scene. Next, let's look at PaCO2. This value is predominantly controlled by the lungs. Increase ventilation and you breathe off CO2. See how the equilibrium shifts to the left, causing H+ to decrease? That's respiratory alkalosis. All right, back to the scene. Low PaCO2 in the setting of hyperventilation is symbolized by the low carbon fumes, close to the ground. Remember, we're blowing off CO2 here. But don't forget about that last part of the ABG, bicarb. Remember Gapwise's bicarb falling into the crevasse? We're bringing it back to represent low bicarb. You see, in the setting of respiratory alkalosis, the kidneys kick in, increasing bicarb excretion and decreasing bicarb production. Remember, in most cases, when a bicarb is lost, its corresponding proton is retained. This helps combat alkalosis, though the kidneys can be pretty slow, and this response can take days. All right, let's look at a few pathologies that can cause hyperventilation and decreased PaCO2. First of all, notice how high he is on those alkaline falls. The air has gotta be thin up there. At high altitude, the decreased oxygen content of the air causes hypoxemia. peripheral receptors in the carotid and aortic bodies sense a decrease in PaO2 and stimulate the respiratory centers to increase ventilation. Another classic cause of hyperventilation is pulmonary embolism. Both the ensuing hypoxemia as well as direct irritation in the lung activate the respiratory centers, resulting in increased ventilation. Notice, too, how Murray looks a little anxious and sweaty as he peers down from the tall cliff. Hyperventilation is a component of panic attacks, which can be seen in generalized anxiety disorder and panic disorder. And Murray's inhaler? That's there to remind you of asthma, which is kind of like a combination of all of the above. Hypoxemia, lung irritation, and anxiety can all stimulate the respiratory centers to increase ventilation during an acute asthma attack. And last but not least, aspirin. Yeah, I know. We saw it down in the gorge with metabolic acidosis. But wasn't it pretty clever of Murray to disguise himself as a gork before making his way up the falls? Ingenious. So aspirin is way up here too, because it turns out aspirin directly stimulates the respiratory centers to increase ventilation. So early in aspirin toxicity, you'll actually see a respiratory alkalosis. The increased anion gap metabolic acidosis that we saw below is slower in onset. All right, I don't know about you, but that's about as much traveling as I can take in one day. I think it's about time we set up camp. Maybe get a stew going. Get some fresh taters in there. You know, potatoes.